All right, welcome back to section 3.4, our last section in chapter 3. So we're going to be talking about applications of the derivative, particularly in the fields of business and economics. So the first thing we're going to talk about is the concept of rates of change in the realm of cost, revenue, and profit. So in business, the word marginal is equivalent to the instantaneous rate of change, which is just another way of saying the derivative. So when we talk about the concept of marginal revenue, marginal cost, and marginal profit, we're talking about a change in revenue or cost or profit associated with the selling of one additional unit. So that's a key theme here. So remember, the derivative gives us that rate of change. So the marginal revenue, cost, and profit give us that change. And we abbreviate them, of course, MR, MC, and MP for marginal. So with the derivative, it's telling us if we were to continue, like if you think about it in terms of x and y's, if we increase x by 1, how much is the output changing, right? We're looking at how quickly it's changing, the rate of change. We're doing the same thing here, but with money coming in, going out. So if we increase our quantity sold by 1 unit, how much is our revenue changing? How much is our cost changing? How much is our profit changing? So we're asking the same question that we've been asking about derivatives, but now we're throwing a lot more context into these equations. So let's look into some examples here. So the revenue realized by a company on the sale of X units of its product is given by the revenue function R of X, given here. Compute and interpret R of 70 and R prime of 70. So we can go ahead. The computation is simple enough and certainly would be good work for a calculator. That number is 373,800. For our prime, let's find the derivative function first. So that's 3x squared plus 8x plus 160. So then r prime of 70, if we plug 70 into there, we get out 15,420. Now, when it comes to the interpretation of these, the 70, the value inside here, is an x value. So we're looking at x units of its product. Okay, so we're talking about the sale of 70 units. So they sell 70 items of whatever they sell. The amount of money we get out from R is revenue, right? This is how much money we have coming in when we sell 70 items. R prime, which is the same thing as marginal revenue, this is the change in revenue if we were to add an additional item to sell. So let me just pull this down here. So when they sell 70 products, they make $373,800 in revenue, and the additional revenue by adding one more unit is approximately $15,420. Okay, so again, our revenue, so we've got 70 items. Our revenue is $373,800. And the additional revenue by adding one more unit, so the 71st unit, is approximately this much money. Okay, so that would be our change in revenue by adding the next item. the concept is the same regardless of which value we're looking for. So the cost to a company to produce X units of a product is given by this cost function. Compute and interpret C of 600 and C prime of 600. So same idea here. So we have C of 600. You just plug in 600. We end up with 11,425. C prime of X. So bring down the 2. That's negative 0.07x plus 40. So C prime of 600 is actually negative 2. So kind of a unique situation here where that marginal is actually going down. So to produce 600 units costs $11,425, and adding one additional unit, the 601st unit, results in a decrease in cost by $2. So don't ask me how that would work in practicality, but based off of the formula that we are given, their production formula, then this is what it's telling us. So we have their total cost, and if they were to add an additional unit to sell, their cost would actually go down ever so slightly. Now, when we want to bring profit into the mix, that usually adds an extra step into our process here, because oftentimes we're not given profit, we're just given cost and revenue, but we can find profit. So the cost to a company to produce X units of a product is given here. Revenue they expect to realize from the sale of X units is given here. If P of X is the profit realized on the sale of X units, compute and interpret P of 20 and P prime of 20. So remember, profit is revenue minus cost. It's the money coming in minus the money going out, and it's whatever you have left. That's the profit. So we're going to take the whole revenue function minus the whole cost function. You have to be really careful when subtracting because you're subtracting the entire cost function. So that negative is going to distribute to each term in that expression. So please be very careful, very mindful with those things, because those are the easy places to make mistakes that end up messing up your final results. But if we do the subtraction, we get negative 0.02x cubed minus 0.6x squared plus 31.5x minus 150. So to find P of 20, we would substitute in the value of 20, and that is just going to be 80. And then for P prime of x, take the derivative, so negative 0.06x squared minus 1.2x plus 31.5. And P prime of 20, again, substitute in 20, you get negative 16.50. So when we are selling 20 units, because it's X units, when we're selling 20 units, the profit we're making is $80, and the change in profit to sell an additional unit above 20 would be negative 1650. So can't really get this to... Okay, we'll just move it out. So selling 20 units gets $80 in profit, and making a 21st unit would lose $16.50 in profit because the value is negative. So if you're this company, you definitely do not want to produce that 21st unit. So for whatever reason, it seems like their costs go much higher, and their revenue seems to drop at the same value there. So they would end up losing a significant portion of their profits by producing that 21st item. So 20 seems to be the threshold for them. Now let's look at one that's a little bit different. So sometimes it's up to us to kind of construct the formulas. We're not necessarily just given them every time. So this one, there's a lot of pieces. So let's read through this first, and then we'll kind of assemble it all together. A company estimates it can sell 200 units each week of its product if it prices each unit at $10. Or sorry, that's 2,000. 2,000 units each week if they price it at $10. However, its weekly number of sales will increase by 50 units for each 10-cent decrease in price. Okay, so every time they decrease their price by 10 cents, they will sell 50 additional units. So, and that may sound like a good deal. Like, well, of course you would like lower the 10 cents and sell those extra units. The problem is that you're now making less per unit, and so you have to figure out where the balance is. And that's where a lot of these formulas come from, is figuring out the balance and how to maximize profit. The company has a fixed cost of $800, and the cost to make each unit is 80 cents. Find the level of production. So we're looking for level of production. This is just saying how many. Like how many would they sell in order to maximize profit if the company must produce and sell between and including 2,000 and 3,500 units. So we're putting boundaries on it. So we're trying to figure out how many units they should sell. And in turn, we're going to figure out what price they need to sell them at. So let's see. We're going to establish some variables here. So this is kind of like optimization, like the stuff we saw in the last section. We're going to let X be the number of units sold, and P will be price. Okay, and this is a lowercase p because we use the capital P for profit. Now, if we're trying to figure out what X is the number of units that they sell. So they currently sell 2,000 units, but they could sell more units, right? 50 units for every 10-cent decrease in price. So we're going to say they could sell 2,000 units plus 50 units times the number of 10-cent decreases. Okay, now the way to write this, it's a little weird looking. Let me put it and then we'll explain it. So it's going to be 10 minus P over 0.10. So this expression right here is this is the price difference and then it's divided into 10-cent increments or 10-cent groupings. So for example, if they decided that their price was going to be $9.80, we take 10 minus 980 divided by 0.10. That's 0.20 minus 0.10, which is 2. that resulted in 2 price drops of 10 cents each. Okay, so 2 price drops of 10 cents each times 50 would be 100 additional units that they sell. Okay, so this formula is the one that we're looking for. So this is going to tell us how many units are sold. Now, in order for us to work with revenue, cost, and profit, we actually need to have them written in terms of X. So we're going to kind of flip this around a little bit. We're going to solve for P. So we subtract the 2,000, we multiply by the 0.10, divide the 50, subtract the 10, multiply -1. So we do all of that, and it actually doesn't work out so bad. We just get 14 minus 0.002x. Now, the reason that we need that is because we're going to find profit. In order to find profit, we need to find cost and revenue. So we're going to get, so revenue is price times quantity sold. So that's 14 minus 0.022x times x. So that's 14x minus 0.002x squared. Cost, I have here in yellow, the fixed cost is 800 plus 80 cents per unit sold. And profit is revenue minus cost. So this is our capital P of X. So that's revenue minus cost. So if we combine the like terms there, we get negative 0.002 x squared plus 13.2x minus 800. And this is the formula that we're going to work with. So like with a lot of these types of problems, the setup is crucial. It takes up a lot of the time, and it's a huge part of being able to solve them is just being able to set them up properly. Because now we can go ahead and take the derivative. So that'll be negative 0.004x plus 13.2. Set that equal to 0. We end up, that gives us x is 3,300. And so we verify by choosing values to the left and right to check for positivity and negativity, bearing in mind that we're bounded between 2,000 and 3,500. So not really to scale, this number's like way up here. But if we check the values, we do get positives and negatives in the right places. So now, what did the question ask? Find the level of production that maximizes the company's profit. And that's it. So we can say maximum profit occurs when they sell 3,300 units. And like with all these cases, if you were curious about what that profit actually is, like what is the maximum profit, it's $20,980. So, but again, the question didn't ask for it, but if it did, we could absolutely get that. All right, we are going to move forward with one final kind of major topic here for us to talk about. and that is the concept of elasticity of demand. So, elasticity of demand, this is the measure of the size of the response in a variable to the change in another variable. So we say if a change in input results in a large change in output, the relationship between the variables is said to be elastic. And if a change in input results in a small change in output, the relationship is said to be inelastic. So when you think about the word elastic, right, you think of things like a rubber band or something, right? Something that you can pull on and stretch. And if you pull on a rubber band and it stretches really, really far, right? It has a big change on the size, the shape, whatever, then that's a highly elastic rubber band, right? So if a change in the input results in a large change in output, the relationship is elastic. If, on the other hand, you take like a metal ring, something like that, and you try to pull on both ends, if you're really strong, you might be able to get it to bend a little, but it's not going to stretch out like a rubber band is, right? So if a change in input results in a very small change in output, it is said to be inelastic, right? It's inflexible. It's unwilling to move or change very much. We're going to apply this concept to elasticity of demand, also known as point elasticity of demand. This is abbreviated using a Greek letter epsilon. It's like a Greek letter E, so E for elasticity. And it is defined mathematically as elasticity equals negative P over Q times dq dp. Some versions of the formula, you can see this uses x, like negative p over x times dx dp, something like that. I believe our text, though, uses p and q. This is where q is the original quantity demanded, and p is the original price per unit. Okay, but this is our formula for elasticity of demand. So it relates the price being charged, the quantity being demanded, and the rate of change. So how quickly does the demand change based on the price that we're charging? Okay. So point elasticity measures the elasticity at a particular point and is interpreted as the percent change in the demand for a 1% change in the price. Okay, so what we're basically saying is whatever number we get out of this, if I raise my price by 1%, this number is going to tell me how much the demand is dropping. Okay, how much demand is decreasing. So when we talk about products and their elasticity, products that are highly elastic, products that have large swings in demand based off of changes to their price. These would be things that would be more like luxury items, right? Things like, like say TVs, for example, right? If a TV company like Samsung or somebody decided that they were going to start selling their TVs for significantly higher amounts of money, a lot of people would probably just not buy them, right? They would just say, "No, I've got one. I'm good. I don't need to buy another TV right now or look at a competitor," or things like that. A lot of luxury items have very elastic demand. Things with inelastic demand would be things like necessities. So things like groceries, household necessities, So because for example, we've had a lot of issues with egg prices. Egg prices have been going up and down, fluctuating a lot. Eggs a year ago started off at maybe like $3 for a dozen eggs. By the time we hit, this year, now it's up to like $7 or $8 for a dozen eggs, and the prices keep going up, but people keep buying eggs. Because those are things that they need. And so they're willing to just kind of eat the price difference, so to speak, and spend the extra money. And so the demand is not going to drop very much, even though the price goes way up. Other examples would be things like cars. Luxury cars are usually going to be considered elastic because I'm not necessarily going to shell out the extra percentages of money for a luxury car, but cars in general in today's market are usually considered a necessity for a lot of people because you need it to get around to everywhere. Probably the most inelastic product out there is gasoline for cars. Because, if you've noticed, gas prices fluctuate a lot. It's been going up over the last many, many years. Gas is something that no matter how high they raise the prices, people still buy it, right? Because you need it in your car in order to get around. And so that's one that is highly inelastic because the demand is not going to drop very much at all, even if they raise the prices. So let's look at an example here. So a company estimates that the weekly sales Q of its product is related to the product's price P using this function where P is in dollars. Currently, each unit of the product is selling for $27. Determine the point elasticity of demand of this product. So we know that currently they're priced at $27. The quantity demanded at $27 would be 4,500 over the cube root of 27 squared. I know that looks scary, but the cube root of 27 is 3. 3 squared is 9. So it's 4,500 divided by 9, which is 500. We also need the derivative. So the derivative of this function. So actually, let me rewrite the function first. So we have Q in general. Let's see, that's going to be, I'll rewrite this as a power. 4,500 times P to the negative 2/3. Okay, so think about properties of exponents. Make sure you're okay with that switch, because this now we can go ahead and take the derivative of. So dq dp, we're going to bring down the negative 2/3. So that's going to be the 3, we'll make that 1,500 times 2. So negative 3,000 times p to the negative 5/3. So that's negative 3,000 over the cube root of p to the 5th. Okay, just putting that in consistent notation. Let's see, we're also going to need the derivative evaluated at the price. So evaluated at 27. So that's negative 3,000 over cube root of 27 to the 5th. So that gives us 3 to the 5th is a big number. Let's see, it's 27, 81 times 3, so 243. And then divide that here. It's not going to work out to a clean whole number, but that's okay. It is negative 12.35 approximately. So these are all the pieces we need. We have P, we have Q, and we have the derivative. So now we're going to get the elasticity negative P over Q times derivative of Q with respect to P. And that will be approximately 0.67. So about 2/3. Okay. So if we look at this number, so this is our numerical value for point elasticity. What this is telling us is that if we increase the price of this product by 1%, the demand for this product will drop by 0.67%. Okay, so it'll drop by less than 1%. And that's pretty good because as a company, if we're trying to raise prices, we don't want to lose all our customers by raising the price. So this is saying that if we raise the price by 1%, we're losing less than 1% demand in our product. So that would be fantastic as a company. So again, if the price of this product is raised by 1%, demand will decrease by approximately 0.67%. Okay. So price is raised by 1%, demand will decrease by 0.67%. This product is inelastic at this price. So for an inelastic product, that means there's not a big change in demand when the price gets changed. Okay, it's not very responsive, which as a company is a good thing because then you want to be able to raise your prices and not lose all your customers. Now, I do mention that this product is inelastic at this price. That is a huge caveat to this. If the price they were charging isn't 27, all of these numbers change. Okay, because all of these depend on that 27. So if they start charging a different price, their elasticity is going to look different. If they're already charging, $100 for this product and they're supposed to be charging 27, raising the price from 100 to more, you're probably going to lose more customers that way, right? Because you're already charging. Like if I'm going to buy, I'll stick with the TV example. If I'm going to buy a TV and the company's charging $500 for the TV and they want to raise the price by, a percentage, so $5. Like, okay, I can stomach a $5 increase on a $500 TV. If the company is charging $5,000 and then they want to increase the price by 1%, that would be a $50 increase. But if I'm already struggling to pay $5,000, maybe that extra $50 is just kind of puts you over the edge, right? Or maybe they're raising it by 2%, 3%, whatever the case may be. The price makes a difference in the elasticity. And on the flip side, if they were only charging, $2 for the product and the customers felt like, oh, if they charged more, I would still be willing to pay for that. Then you can have much, much smaller of a drop in demand as you go. So what does this mean in terms of revenues, elasticity, inelasticity? Let's see how all of this kind of ties together. So here's some conclusions. So if our epsilon value, our elasticity value is greater than 1, that means that the marginal revenue, R prime, is less than 0. So that means the additional revenue from adding one extra item is negative. It's going down. Okay. So this means that total revenue falls with price increases and rises with price decreases. Okay, so if our epsilon value is greater than 1, our revenue, anytime you raise the price, you're going to start losing revenue. Okay, and anytime you lower the price, you're going to gain revenue. This is what happens when demand is elastic. Okay. A change in price results in a large change in demand. So again, you raise the price, your revenue, the amount of money you make, falls. You're going to lose too many customers, and you're going to lose all that extra revenue. If we go down, I'm going to skip the second one for just a sec. If our elasticity value is a fraction between 0 and 1, then R prime of P is positive. So our marginal revenue is positive. So that means that total revenue rises with price increases and falls with price decreases. So demand is inelastic. So this is kind of the flip side of this, where we have a price being raised, but because the demand is inelastic, you're not going to lose that many customers. So you're going to keep most of your customers, and they're all going to be paying more money when you raise the price. So your revenue goes up in this case. Okay, so we have elasticity greater than 1. We have elastic demand that's going to rise and fall very quickly. If you have elasticity between 0 and 1, demand is inelastic, and it's going to rise and fall with the price increases. The revenue will, I mean. So elasticity should always be positive. That's one thing to take away from this. A lot of people somehow start getting negative numbers out of here, but notice it shouldn't dip below 0. It shouldn't even hit 0. It should be non-negative. Everything here is centered around the value of 1. If elasticity equals 1, marginal revenue, R prime, is 0. So if R prime is 0, that means that adding one additional item does not change your revenue. So the revenue is unaffected by changes in price. And we could get a little bit deeper into this if we were kind of taking more time on this topic. But basically, this is where revenue is maximized, is when elasticity is 1. Demand in this case is what we call unit elastic. Unit, like 1, because we get an epsilon value of 1. This is the sweet spot. This is what we're aiming for. Like I said, this is where revenue gets maximized. So if you have a highly elastic product at whatever price you're charging, you should be lowering prices to make more money. Okay? Elastic products, you should lower your prices to make more money. Inelastic products, you should be raising your prices to make more money. If you have a product that is unit elastic, that means this is as much money as you can be making. Okay, so anytime we have elasticity values that are above or below 1, you want to try to, as a company, you want to try to either raise your price or lower your price and try to get that elasticity to 1, because that's the one that's going to give you your maximum revenue. Consider the previous example. So the example that we worked on the previous page. So explain the result in the context of elasticity of demand. So we found in the last one that it was about 0.67, right? And this value being less than 1 is inelastic. So this means that revenue will increase as price increases. Okay, so this company should raise their prices because that will raise their revenue also. If we want to find how much that revenue would change, we can actually calculate that. So the demand, if we go back and look at the example again, so the current quantity demanded is 500 units. So we would take 500 units minus a 0.67% drop in demand. So as a percentage, that's 0.0067, like that, right? Because it's 0.67%. So as a decimal, that's that number, times 500. So this is, just label this here, this is quantity demanded, and this is minus 0.67% drop in demand. This is approximately 497 units. So when we talk about them raising their prices by 1%, it will result in them selling 3 fewer units. Okay, so for revenue, if they're selling 500 units at $27 per unit, they're currently making $13,500. So this would be current revenue. But if they made this change, they would be selling 497 units, and the price would be 27 plus 1% of 27. So 0.01 times 27. So this is 1% increase of 27. So that's 497 times, this is 27.27. That would be the 1% increase. And that would be approximately $13,553.19. And that would be their new revenue if they were to go through with this price increase. So again, let's just kind of reestablish what was stated here. The elasticity is less than 1. It is inelastic, meaning that if they want to raise their revenue, they should raise their prices. So we found that if they raise their prices by 1%, so they charge $27.27, they would sell 497 units, and they would make $13,553.19 instead of $13,500. So they're making an extra 53 and change dollars because that's how it balances out. They lost 3 customers, but all the remaining 497 are paying slightly more. So that small dip in demand resulted in more revenue for the company. Next, we're looking at part B. Suppose the function relating the variables was this. So that's Q equals 97,533 over the fifth root of P to the 24th power. So these results are going to get more extreme because the numbers get bigger, the powers get higher. So let me just, actually I'm going to make a little more space in this. So if you want to get the practice of calculating elasticity, please, by all means, you can pause it, try to calculate elasticity for this item. Also, again, at the given price. So we would get elasticity would be approximately 4.8. So this is highly elastic, right? Because it's all about whether the value is close to 1 or not. This value is certainly greater than 1. It's almost 5 times that. So then this means that a 1% price increase results in a 4.8% demand decrease. So then for our demand, we would have 500 minus 0.048 times 500. Right, so that would be, see, 500 times 0.048 is 24. So 500 minus 24 would be 476 units. So they're only selling them, they're only selling 476 units in this case. In terms of revenue, if they want to, so let's just go back real quick. So before we had the price of 27, we had the Q, we got to be 500. The reason that Q was 500 here was because of this formula. If Q is going to be 500 in this case, the P value that makes that happen is actually not 27 anymore. It's actually $3. So revenue is going to be 500 units times $3. So, and this is again, new price, new formula. So in order to get a quantity demanded of 500, they'd have to charge $3. So we would get 1,500. So then our total revenue would be 476 times 3.03, right? That's the 1% increase in price. And that's going to be $1,442.28. So we see that before they changed the price, they were making $1,500. They had 500 customers. They were charging them $3 each. They had $1,500. Then they raised the price by 1%. This is a highly elastic value. at this price. So the price went up, but the customer demand went way down. They lost 24 customers, and in the process, they ended up losing almost $60 in revenue. So even though the remaining 476 customers paid more, it wasn't enough to offset the losses from losing that many customers. That's what happens when you have such a high elasticity of demand. And then let's look at part C, our final one. So suppose the function is this. So very different. Q is 62,500 over P. So no radicals, just the P down in the denominator. This one, if you calculate elasticity, it does work out to 1. So I would encourage you to try that out. And this means that a 1% increase in price causes a 1% decrease in demand. And that's what we want. Okay. So this is where we can maximize that revenue. So I raise my price by 1%, I lose 1% of my customers, but it all stays the same as far as revenue goes. So what happens is our demand goes from 500 to 495, but our price goes from 125, again, updated price because of the updated function, to 126.25. Okay, so this is the price. So for the revenue, we take 495 times 126.25, or you can take 500 times 125. They both equal $62,500. So the revenue would be exactly the same, because even though we lost 5 units demanded, we lost 5 customers, so to speak, the amount being paid extra by the customers we still have balances out perfectly. And so that is how we can maximize our revenue. But that brings us to the end of section 3.4, the end of chapter 3. Thanks for bearing with me on this one. I know this section is a bit longer because we have several topics to discuss, but that is the end of our chapter. So I will talk with you all in the next chapter very soon.